In this video, I'd like to take a look at a one-sample t-test and how to proceed through the hypothesis testing. So the example that I have here is below we have brain volumes, cubic centimeter, from a random unrelated subjects used in a particular study. We used 10, very small sample. And therefore, we're going to take a very tight type 1 error of 0.01, or we're going to take a risk of only 1%. That'll be our significance level for our test. We're going to test a claim that the population of brain volumes has a mean equal to 1,100 cubic centimeters. So that's the number that we're looking for. And since it's equal, our claim here is going to be in the null hypothesis because we want status quo. We're hoping for no change from what we expect. And so the mean is equal to 1100. Notice I'm using the symbol for mean here, which is mu. The alternative is the opposite of that, which is that it is not equal. So if we end up in a risk situation, we're going to claim that the null is not, we're going to have to reject the null in favor of the alternative. We're going to use a significance level of 0.01. So this is how we start. Once we get to this point, notice we are no longer dealing with brain volumes. We're dealing with just numbers. So this is the mathematics part of it. Okay, and that's all we want to look at is the mathematics part of it until we get to the final statement. So the test statistic for a one sample t-test, and since this is a not equal, it's a two-tailed test. If it were greater than, if this in here were mu greater than, if we're trying to prove something greater than or less than with our alternative, then this would be a one-tailed test. But in this particular case, it's a two-tailed test. So our two-tailed test, the formula for the t-statistic is x minus mu, x being what we get for our calculations in our sample, minus the mu, which is what we're trying to prove, and we're going to divide that by the sample standard deviation divided by the square root of n. Now be very careful here because we need to find the standard errors, the sample standard deviation divided by the square root of n before we do any division of the difference here. So be very careful when you do your calculations there. The critical value that we would use if we're going to do our calculations with t-statistic and the critical value is found on the standard t-table. So I have one posted here, and what I did was you start here. This is the degrees of freedom. Remember, degrees of freedom is always one less than how many there are. The count, which I've done here, is the count of those numbers, which there are 10. And so 9 is my degrees of freedom. So it's this row that will house the information that I'm looking for. It is a two-tailed test. So to decide what column I should be looking at, I look under here under two-tailed test and I find the significance level that I'm looking for my risk, which is 0.01. Where the column and the row intersect is 3.250. So my critical value, since this is a two-tailed test, is a plus or minus 3.25. So anything between those two is going to fail to reject the null hypothesis. Anything outside of 3.25 will reject the null hypothesis. So the next step is then to perform the calculations. And I perform the calculations. First, I need to find the mean. And I do that by using the function average. And I put in average and then the numbers. I just simply highlight my set of numbers here. And you'll see they're highlighted. And then my standard deviation, notice that I've used my function STDEVA. That found my standard deviation. And again, in the parentheses, I simply highlight that and it puts in the range for me. So now I have the pieces that I need to put into the formula. And there's my formula. I've substituted x. Notice I put parentheses around this. X, my x value being my mean, minus the mu, which is 1100, divided by, and now I put parentheses around this because remember, this calculation, this division here has to be done before I can do this other division. That's order of operations. And so I have 117.45 rounded, divided by the square root of 10. And when I do that calculation, I get 0.81. Now, to find the p-value, if I want to do my comparison for my statistical conclusion with p-value, my p-value is done with the function t.distribution.2t. I put in the t statistic that I have, and I put in the degrees of freedom, which in this case is 9. Now, once I have done that, I have performed all my calculations. Now I come down here to my statistical conclusion. I can do it one of two ways. I can either compare t to the critical values, in which case I'm comparing a 0.813, and it happens to fall between 3.25. So my statistical conclusion would be to reject the null hypothesis. Or I could compare the p-value to the level of significance, which is the most common done in most testing research today. And that's going to be a 0.044, which is greater than 0.01. And again, I would fail to reject the null hypothesis because the p-value is greater than. Remember the rule. If the p is low, the null must go. If the p is high, the null will fly. And so in this particular case, I would fail to reject the null hypothesis. At this point, I am done with the mathematics, the statistical part. I now have to take my statistical conclusions and put them into a vernacular that the public will understand. And so I make the statement that there is not sufficient evidence to support the conclusion that the mean brain volume is different from the level of significance. And that's the end of this. If you have any questions on these steps, please don't hesitate to post questions and let's discuss it in more detail. Thank you.